Hi, my name is Sebastian Matteau and welcome back to this second video tutorial in the series on deep learning with Keras in Python. So in the first tutorial we reviewed some basic concepts and terminology related to deep learning, and now in this second tutorial we're actually going to apply that knowledge and build our own very simple basic neural network with Keras. You can find the text version of this tutorial on python.coxsci.nl, so if you want to review the code that we're going to create or read a little bit more, then please visit that website and you can find it there. So what are we going to do? The network that we will create is pretty simple, so it will not yet be a deep neural network, but it will sort of provide us with the basic tools that we need in later tutorials to work with bigger networks, with deeper networks. So we will create a simple 3-layer network. And as input to this network, we will give individual numbers between 0 and 1. So floating point numbers between 0 and 1. And each number is one observation. So we will give it one number at a time. And then the task of our very simple network is to tell whether the number is either less than 0.05 and classify that as the category 0, or equal to or larger than 0.05 and classify that as the category 1. In other words, we are going to train our simple network to perform a rounding operation on numbers between 0 and 1, right? So that numbers less than 0.5 are rounded down to 0, and 0.5 and higher is rounded up to 1. That's what we're going to do. How are we going to do that? Well, let's start data first. So let's start with defining our training data and the labels. And the labels is basically the predicted expected output. So we will train our network by giving it numbers and telling it what should come out of the network, right? The predicted output. So let's create description, create training data and labels. And we're just going to create a NumPy array for our training data. Import NumPy SNP. Now, we're going to create 10,000 numbers between 0 and 1. So that's a sizable training set, right? We will feed 10,000 observations into the model, and each individual number will be one observation. So let's start by simply saying data. So the data will be our training data, is np.random.random. And then we need to tell this function np.random.random how many random numbers we want. And we say 10,000 because we want 10,000 random numbers. Then this function, in case you don't know, automatically gives back random numbers in the 0 to 1 range. Are we done here? No, not yet. Because the shape of our data, if we specify it as such, is incorrect. Let me run this. Up. And then here in the console, I will type data.shape. I'm assuming that you are familiar with NumPy arrays and that they have a d-type that indicates the type and a shape that indicates how many dimensions they have and how big each dimension is. If not, I actually have a tutorial also on NumPy on python.coxsci.nl. And here in data.shape, you see that this data is a one-dimensional array and its one dimension has a shape of 10,000. That's not yet good for our model because our model expects at least a two-dimensional array. And the reason is as follows. The first dimension corresponds to the observations. So the first element of the first dimension will be the first observation, the second element will be the second observation, etc. Then the second dimension will contain all the numbers that are part of that observation. So say that we actually were going to train, for example, a network to perform an addition. Then we would feed two numbers into the network. And then our input, or our observation, would consist of two numbers. And if we would then train it on 10,000 additions, we would have an input array, a data array of 10,000, so 10,000 observations as the first dimension. And the second dimension will be 2, because we have two input numbers. So it will be 10,000, 2. In our case, we have only one value per observation, but the structure of the array still needs to be the same. It still needs to be two-dimensional. So what I can simply do here is change the shape of the array, say data.shape is 10,000 observations, comma, and one value per observation. That's what this means. And that's the correct format for the input for our model. Different models have different inputs, but our model requires this input. Then we're going to define our labels. So labels is, and what should labels be? Well, first thing that we can do is say, okay, the labels is equals to the data is larger than or equal to 0.5. If I execute this, I press F9, it's the same as clicking on the quick run button here. And then here in the terminal, I inspect labels. You see, it's almost good, but it is not it is an array of Boolean values, false and true. That's not good for our model. Our model wants integer values, 0 or 1, to correspond to the categories, category 0 and category 1. So we need to, this is almost correct, but we're simply going to say, we take this Boolean array that results from this comparison, and we turn it into an integer array. Now, if I run it and I print out data, you see here, right, for our data, let me scroll up a little bit, move up. You see this is the first input observation, this is the second input observation, and so on. And for the labels, that corresponds to how they should be classified. So the first input observation happens to be smaller than 0.05, so it should be classified as 1. Here, as the third, you see, we have an input observation that is larger than 0.5, so it should be classified as 1. Sorry, this one should be classified as 0, this one should be classified as 1. Okay, so now we have our data and our labels in the format that we can use to train our model. But we don't have a model yet, right? So let's create a model. So creating a model in Keras is very simple. We're going to, let me actually pull up Perceptron, load it. An image to indicate the kind of model that we're going to create. Our model will have this input layer of one neuron, and that corresponds to this one input value that we put into the neuron each time. Then we have a hidden layer of 8 neurons, and it is densely connected. This means that each neuron is connected to all neurons in the previous layer. Well, there's only one, but they're all connected. And then we have an output layer of 2 neurons, and they're again densely connected to each of the 8 neurons in the hidden layer. So that's the structure of the network that we're going to create. Why does it have this structure? Well, that's fairly arbitrary, actually. You can create all kinds of networks with different layers and different sizes, and for this simple task, it will actually not make a very big difference. So determining network architecture is actually more of an art than it is an exact science. But when you have a simple task, it's very difficult to go wrong. Basically, many networks will be able to learn this just fine. Okay, let's close this. All right, here's a build the model. So we're going to use 2 classes from Keras that we're going to use to build the model. One class that corresponds to the model itself, and one class that corresponds to the layers. So from Keras import sequential. That's going to be our model. Why is the model class called sequential? Well, because it corresponds to a stack of layers that is purely sequential. You can also think of model architectures that, for example, that have recurrent connections or are very complicated in one form or another. You wouldn't be able to build those with this sequential class, but the sequential class is very good at building these kinds of simple stacks of models, of layers. So it's not sequential in time or anything like that. It is sequential in its layers. And then from Keras.layers, import dense. So we're going to add densely connected layers to our model. And then creating the model is actually very simple. You can simply say our model equals the sequential class. And then the sequential class expects a list of layers. What kind of list are we going to feed into it? Well, the first layer that we're actually going to define is not the input, but it is the first hidden layer. It goes like this. I will type it and then I will explain it. So we say 8 units, input shape is 1, up, activation is relu. So what does this mean? So this corresponds to our hidden layer, right? Our hidden layer is not really the first layer of our network because we also have an input layer. But we specify the input shape here, and that implicitly creates an input layer. And what is our input shape? Well, it is an array of size of shape 1 because it consists of only one number. Then here we have an activation function, and this is one of these examples, and you will find many of them, where there's pretty complex terminology used for pretty simple ideas. So ReLU refers to rectified linear activation unit. And what that in turn means is that the neurons in this layer are not allowed to send negative output. So it is possible for a neuron to, for example, get a lot of negative input, right? For example, because it is connected to layers that are inhibitory. But then basically the minimal amount of output is 0 for these neurons. So you can also think of it that the output of each neuron in this hidden layer is the max of 0 and the actual stimulation of the neuron, if that makes sense. So that is our hidden layer. And then we say, okay, our output layer consists of 2 units. We don't have to specify the input shape now. Why not? Well, because we've already specified the previous layer, so Keras will be able to infer what the input for this layer looks like. We do have to specify the activation function, and this activation is called softmax. What does this mean? It means that the output of the neurons in this layer, in this output layer, is squeezed to be in the 0 to 1 range. So even if the stimulation of the neuron would be very negative, then the output would be 0. And even if it would be super high, say 1,000,000, then it would become 1. It is essentially sort of a sigmoid where the output is sort of squashed into the 0 and 1 range. I hope that makes some kind of sense or that you intuitively feel what I mean. And why is this useful? Well, it is useful because then we know that our output layer, it behaves very predictably, namely containing values between 0 and 1. Okay, this is our model. This is how we can define it. If I run it now, you will see, okay, it takes a little moment to import, and then we're done. And we can also print out a summary of the model. Let me do that here in the console directly. If I say model.summary, up, we get a description of what our model looks like, a textual description, but it's still quite easy to read. So it starts with our hidden layer, the one with 8 units, and that has 16 parameters. Why? Well, because each of the 8 units is connected to the input unit, right? The input neuron that we're not specifying. So that's already 8 parameters because each connection has a weight. And then each neuron also has a bias, which is kind of like a baseline level of activity for the neuron. And that's also 1 parameter. So that's another 8 parameters, right? So for each of the 8 neurons, there are 2 parameters, and we end up with 16 parameters here. For the output layer, this one has 2 units, actually has 18 parameters. Why? Well, because each of the 2 units has first a bias, right? So 2 parameters already. And each unit is also connected to each of the 8 layers in the layer, each 8 neurons in the layer before, so 8. So that's already 2 times 8 is 16. So that adds up to 2 plus 2 times 8 equals 18 parameters. So our model has 34 parameters in total. It's already quite a lot, right? So there are 34 values that need to be fit during our training. Okay. Is our model done now? No, not really. We still need to compile the model. What does it mean to compile the model? Well, it means essentially to make the model ready for training. Compile. So if you're wondering why do I type these sort of triple quoted multi-line strings, they are used, Rapunzel, my text editor, uses that to distinguish cells that you can run. So everything between this comment and this comment is considered one cell that I can run in one go. And everything below here is considered one cell. So it's basically a way to add comments and divide your code up into cells. Just as a little bit of an aside. Okay, compile the model. Compiling the model is simple, actually, but it requires a little bit of knowledge of what you need to do. So you say model.compile. That's it, essentially. But we need to always specify at least 2 keywords when we're compiling the model. The first is the loss function. Loss. And I'm going to say loss equals, and then something very complicated that is actually pretty simple. Sparse categorical cross entropy. Okay, what does this mean? Well, our model needs to know for every prediction that it makes, basically, for every number that we feed into the model, and then it's going to give an output. For every prediction that it needs to make, it needs to know how wrong it is, essentially. It needs to determine the error of its output, and that's called the loss. Now, the sparse categorical cross entropy loss function, which sounds so complicated, basically just means that for a label of 0, it expects the first neuron to be the most active and the second neuron to be the least active. And for labels of value 1, it expects the second neuron to be most active and the first neuron to be the least active. So say we have our two output neurons, right? And they can be active or not. Say that we're feeding we're feeding the number 0.1 into the model. And then what the model does initially, because it hasn't been trained, is it will actually sort of make both of the output units pretty active. But then we tell it, well, actually what we expect is that the first neuron should be most active and the second neuron should be relatively inactive. And the sort of the deviation between what the model actually outputs in the output layer and what it should output, that is the error or the loss. And that is what the model will try to minimize during training. I hope that makes some kind of sense. So the reason that we have to select this sparse categorical cross entropy is because we have decided, as an arbitrary choice, that we're going to feed labels as 0, 1 categories into our model, and that we have two output units, and these two output units, they need to be somehow mapped onto these labels. I hope that makes sense. Okay, so that's one keyword that we need to specify. The other one is the optimizer, and here I select Adam. So what is the optimizer? That is actually very complicated, but it is basically the algorithm that changes the weights and the bias parameters of the model during learning. So, and Adam is just one algorithm of several that you can choose. So these two things are related, right? So the Adam optimizer is basically changing the weights during learning so that the loss, as determined by the sparse categorical cross entropy loss function, becomes as small as possible. So those things work together during training. Then we can optionally specify metrics accuracy. This is just for visualization. So what this will do is that during training, it will give us some kind of output with the accuracy of the model so that we can see how well it is categorizing the training data. It doesn't really affect the training procedure as such, or it doesn't affect it at all. It is just for visualization purposes, but it's still pretty convenient to do it. All right. So now I'm going to run it. Press F9. Up. We don't get any output. It just compiles the model. And now we can actually train the model. Again, that is quite easy, but we need to know a few things about how this works. Train the model. So just like the model has a compile function, it also has a fit function, model.fit. And the fit function has a few arguments that we need to specify. So let's do that. The X argument is our data. It's our training data. So it's what goes into the model. The Y argument are the labels, so the expected output. We have, for this tutorial and also in future tutorials, we use NumPy arrays for the data and the labels for the X and the Y. There are also a few, the fit function is quite flexible, and there are also a few different formats that you can use to feed data into the model. But you can read more about that on the Keras documentation site. But I prefer to use NumPy arrays in the way that I'm showing you now. Then I say epochs is 10. What does this mean? Well, the number of epochs refers to the number of times that the full training data set is fed into the model. So it goes like this. We have 10,000 observations. They are put into the model, and the model is sort of trained so that the predictions of the model come closer to our labels, right? So that the loss is reduced. That is one epoch. Then we do it again. That's the second epoch. Then we do it again and again and again. And we do it 10 times. So it seems a bit strange, but that's how training works. We don't feed the data into the model only once. We do it, generally speaking, multiple times. And in this case, we do it 10 times. So it's similar to having a for loop with 10 iterations around the model.fit function and then having only one epoch. And I say verbose is 2. That basically specifies that we want to have some kind of output while we're going to fit the model. Okay, so let's show the terminal and run this, and then our model will start training. The first epoch always takes a little while, but then it will go relatively fast. Epoch 1 of 10. Oh, there it goes. Yeah, up. All right, so now it's done training. So let's scroll up to the first epoch. Then you see that at the end of the first epoch, it had a loss, which is kind of difficult to interpret, of 0.6, and an accuracy of 0.5. So it was pretty arbitrary, basically, in its predictions. Then over the epochs, you see that the loss function goes down to 0.11 here, and the accuracy to 0.99. In other words, it is now able to pretty much accurately classify our training data. You see, this will not, for most numbers, it will be perfect. But of course, our model doesn't really know exactly where the rounding boundary is, right? So, for example, if we would feed it a number 0.4999999, maybe it would make a mistake, or 0.5000001, for example. So it will not really reach an accuracy of 1 very easily with this task. But it very easily reaches a high accuracy. I hope that makes some kind of sense. So what is not good about the way we are evaluating the performance of the model now is that this accuracy refers to the accuracy of classifying the data that the model was already trained with, right? So it is circular of sorts. We have a training data set, and then we're training the model with that, and then we're seeing how well the model is at basically classifying observations from the training data set. This is not ideal because there is the risk of so-called overfitting, which I will talk about more in a later tutorial. But basically the risk is that the model will learn the details of the training data set, but will not learn to generalize to new observations. That is called overfitting. It is very unlikely to happen in our example because basically we have 10,000 observations between 0 and 1. So pretty much every number there is, well, of course there are infinite numbers, but a lot of numbers there are between 0 and 1 are fed into the model. So I think it's a pretty, a comprehensive training data set. But nevertheless, it is good practice to create a separate test data set and then to see how well the model does on this separate test data set. So, then we say testing the model. Up. So what is our test data set going to look like? We can say, okay, test data is mp.array, and we'll just give it a few numbers. 0, 0.2, 0.4, 0.6, 0.8, and 1. And then we want it, so these are numbers that are kind of new, right? Our model hasn't necessarily seen these numbers before, although maybe they were actually coincidentally part, of course, of the training data set. And then we're going to generate predictions for this model. Predictions is model.predict test data. Okay, let's run this. Okay, and now let's take a look at what the predictions actually look like, because that's a bit strange actually. Predictions. Okay. Oof. What does this mean? This is what model predictions look like for our model. And the meaning of it is the following. Each basically row here, so the second numbers in the second dimension, they correspond to the activation of the first output neuron and the second output neuron. And this is then for our first test observation from the test set, so for 0. This then would be, so for the last observation, so the 1. But again, the first number here would correspond to the activation of the first output neuron and this, the second output neuron. So what we actually want to know is whether, these numbers, this number is higher than this number, or whether this number is higher than that number, right? We want to know basically which of the two output neurons was most active. Of course, we can just manually decode it, look at it and decode it, but we can also use the kind of convenient argmax function of NumPy, and we can say, I'll do it here, print np.argmax predictions axis is 1. And then for each of these arrays in the axis 1, it will print out the index of the highest value. So if I run this up, you see this is what we get, the 0, 0, 1, 1. This means that for first observation, value 0, the first neuron, index 0, was most active, and also for 0.2 and 0.4, and that's correct, right? So those numbers are classified as being smaller than 0.5. And for the remaining numbers in the test set, you see that it actually, the second neuron, output neuron, was the most active. So these two are correctly classified as being equal to or larger than 0.5. In other words, our model is, for this very small test set, has perfect performance. And that's good, and it's also not so surprising because we have a very simple task. So, as I said, it's important to check whether your model does well, not only on the training data set that it saw actually during training, but also on an independent data set that it wasn't trained with. This, what we did here, creating a test set, is one way of doing that. Another way of doing that is basically during training already, keeping a small part of the data apart and call that the validation set. And then during training already look at whether the accuracy for the validation set also increases along with the accuracy for the training data set, if you see what I mean. So whether during learning, the learning actually also generalizes to a small part of the training data that we've set apart and are not actually putting into the model. And then we can check whether also the categorization of that separate validation set improves as well. So validating the model during training. Okay. How does that work? Well, it again works by calling the fit function. So I will go up actually and here create a new model so that we can start from scratch. Otherwise, if I would continue fitting the model, basically we would build on what the model has already learned, right? And we don't want that. So I built the model and I compile it. And now we have an empty untrained model. And what we're going to do now is say model.fit. And it's quite similar as to before. So we're going to say X is the data, Y is the labels. We're going to have epochs is 10, so 10 epochs. The verbosity, so how much we want to print out, is going to be 2 again. So this is so far the same. And now we say validation split is 0.1. What does this mean? It means that the model will take the last 10%, the last 0.1 proportion of the training data, will set it apart, not use it to train the model, but use it to print out an independent accuracy metric to see if we are not overfitting the model. So let's run this and let's see what comes out. Up here above, we see we're starting again, right? So in the beginning, we already have accuracy 0.7, validation accuracy. So this is the accuracy of the validation training set. And if your model is doing a good job, then over the epochs, both the regular accuracy and the validation accuracy should go up to more or less the same extent. And if I scroll down, you see that here this is definitely the case, right? And after 10 epochs, you see that the accuracy on the original set and the validation accuracy both are very high. In other words, our model is doing a really good job. It is not overfitting, but it is really properly able to round down numbers smaller than 0.5 and round up numbers that are equal to or larger than 0.5. Okay, there was a lot of information. But I hope that you've been able to sort of get a grasp of how you can build a simple neural network with Keras. And building a complex neural network is actually not going to be so different. And we first created a training data set, right? And a NumPy array that needs to match the format that our model expects. A labels array that sort of indicates the expected output of the model that we're going to use for training. We built the model using the sequential class and densely connected layers. We compiled the model to sort of prepare it for training, specifying the loss function, which determines how wrong the model's predictions are, and the optimizer, which is the algorithm used to actually change the parameters in the model during training. Then you fit the model based on the training data and the labels. And if you want, you can use the validation split keyword to set apart a proportion of the data for a separate independent validation set. And we've also seen how you can use the model.predict function to generate predictions for a separate data set that the model hasn't seen before. Okay, well, I hope this has been useful. Now let's move on to the third tutorial, in which we're actually going to use a pre-trained neural network to do image classification. All right, thank you very much for watching.